Aloha. So for this problem, we want to calculate the volume rate of flow given that the diameter of a faucet, which I'll call D, is 1.85 centimeters. And we're told that the pressure head above this faucet here at the bottom of some tank of water is 12 meters. So I'll label that as H. That's like the height of some tank of water, and it's got a little outlet down here. So this will be H, and the diameter, really the diameter of this little faucet here at the bottom. So we can have water in here flowing out of here. So that's the picture to have in mind, and we can calculate, we want the volume rate of flow, which is, you could do like either thinking out of the volume over the time, or like a volume per time, like a volume rate of flow, or the cross-sectional area times the velocity through that cross-section. So that's what we want. We can start using by using Bernoulli's equation. So thinking about this top section up here at the top of this water in this tank, you have the pressure plus a kinetic term, 1/2 times the density times the velocity at the top there, plus the density times G times H at the top there. Being equal to what's happening at the bottom. So the pressure there at this little faucet, like exiting this tank, that's what we're interested in. Plus 1/2 times the density of water times V2 squared. And we're interested really in calculating, we want now like A times V2. This is V2, the water leaving the tank through the faucet, and V1 would be up here, the level dropping a little bit. And we can assume that at the bottom here, the height will be 0. And we can have H1 be H that we're given. So that's at the top of the tank there. And the pressure will be the same because both of these, the top of the tank and the faucet are both open, so they're both at atmospheric pressure. So P1 is equal to P2, and we can get rid of that. You can just imagine subtracting one from the other side, and they're equal. So we can just get rid of those terms. And we can assume that at the top here, the water level is dropping a lot more slowly compared to the speed at which it's leaving the faucet down here, where it has all that water above it. So we can approximate V1 to 0, because basically we just have the potential energy of all the water at the top, assuming this tank is pretty big. So we just have rho GH, which we're given, that H is equal to 1/2 rho V2 squared. So you cancel out the density of the water, and then we can rearrange this so we have an equation for V2. It's going to be the square root of 2GH1. G is the acceleration due to gravity. And the area, we don't know, but the area we can calculate from the diameter here, because we're trying to calculate this volumetric flow through this little faucet entrance here, which has a diameter D. So we're calculating AV, and that is area of a circle, pi r squared. We're given D, so r is D over 2. The diameter is, the radius is 1/2 the diameter, so that's pi r squared, and then we have V2. So you can plug this all in together. And then we have AV, the quantity we want. That's the volume rate of flow through this little faucet at the bottom of the tank. We can just plug in numbers now to get our answer. 1.85 centimeters is really 1.85 times 10 to the minus 2 meters divided by 2 squared times the square root of 2g is 9.8 meters per second squared. We'll use that approximation, and h is 12 meters. So we want everything, all the units to be consistent here. So we'll have final answer. We'll have meters squared as the units here over a second squared, but that's in a square root, so it's a meter per second squared. Then we have a meter squared. So our answer will be in meters cubed per second, which is good. We want a volume rate of flow. And plugging all these numbers into a calculator, you should get 4.2 times 10 to the minus 3 meters cubed per second.